Alrighty, so got all the problems off the practice test pulled up. Work on as many of them as we have time for. Anybody have any in particular you want us to go through first? We can take requests first and then go through them from there. Anybody looked at it yet? Let me get one. 17. Okay. Bear with me scrolling here. Number 10. I got a while to go to. Should have zoomed out before I tried to scroll. 15. Okay. So 17, let's see. A ball is thrown into the air with a velocity of 36 feet per second. Tied in feet after t seconds is given by this equation. Find the velocity when t equals 1. Okay. So that's equivalent of asking us what's the slope of the tangent line at an x coordinate of 1. That one. So then we need to figure that out. Let's see. See what the best way for us to work this is. That one doesn't give us a lot of room to work, so I guess I'll work it out to the side here. So I'm going to take our y equals function and just for convenience, I'm going to call it f of x. Well, f of t, I guess. What we're looking for, we want the limit h approaches 0. We're doing the definition of the limit definition of tangent. So our t coordinates, like our x coordinates, will be 1 here. So we want limit as f of t minus f of 1 over, well, no, I'm mixing my definitions, I'm sorry. We want 1 plus h f of 1. That's what we want. Okay. That's our limit definition. Limit definition of the derivative for the slope of the tangent line. And I'll probably be soft and give that to you. So I'll give you this part. I'm just taking that and filling it in for our information here. We're calling it t. Okay, our t value is 1. So, avalanche over there. Okay. So that's the thing we've got to find. So 36 times 1 plus h minus 16 times 1 plus h squared minus, and if we do f of 1, so we get there, 36 minus 16. So I just plugged in for 1 for t here. 36 times 1 is 36, and then minus 16 times 1, 16. Okay. And start solving for that thing. So let's see. 36 plus 36h minus 16 times, we have to FOIL that out. So 1 plus 2h plus h squared. And then 36 minus 16 is 20, so times 20 each. This is like pretty much the worst one on here, so don't freak out. Okay? There's a lot of them that are easier than this. Let's see. Minus 16 minus 32h minus 16h squared 20 4h. So let's see, 36 minus 16 minus 20, those cancel out. And we have 36h minus 32h, so 4h minus 16h squared h. One of our h's will cancel. That leaves us limit h approaches 0 of 4 minus 16h. What's that limit going to be? Plug in 0 for h. Yeah, so we just get 4. So all that work over our units here, let's see. End up with a velocity of, if I can get this thing to scroll, 4 feet per second. That's, oh goodness, screen's acting crazy. That's sure one of the worst ones, just because it's so long. And you got to know to use the limit definition of a tangent. The reason why we're using the limit definition of a tangent is because just the slope between two, the secant line, right, would be just the slope. And so we're looking for instantaneous slope or instantaneous velocity. So I got another one in particular bugging you? No? I'll scroll back up to 1 then. If you run across one that you need to get to, we may be able to get through all of them. I don't know. Let's see. Especially since we got that one out of the way. Number 1. Just ask us to find these limits looking at the graph. First one is the limit is x approaches 2, and then we got the little minus sign out by the 2. So which direction is that? Approaching 2 from the left. Okay, so if we come in approaching an x value of 2 from the left, what does it look like our limit is on that one? 3. Okay. Not bad, yeah, 3 on that one. Next one's approaching 2 from the right. Coming in down the slope on the right side, so our limit is 1. Yeah, 1 on that one. It does take a minute to figure out their grid lines. And then C, as for just the two-sided limit as x approaches 2, so what's it going to be? Does not exist because, yeah, they're not equal. The one-sided limits are not equal, so Two-sided limit does not exist. D part wants us to find f of 2. So nothing fancy there. We're not doing a limit. It just wants to know if we plug in 2 to this function, what y value we're going to get out of it. So you just look to see where the point on the graph at 2 is. And on this one, it's up here. That's at 3. And E part says the limit as x approaches 4. So we're coming in our graph this way and this way because it's two-sided. So what's that limit look like? 4, yeah, 4. And then it says find f of 4. So f of 4 would be right here. But we got a hole in the graph. So this one's undefined, or it says you can enter D and E. Do D and E. On the test, you could say f of 4 is undefined, and that's good too. Questions on any of those pieces? Okay. Well, I'll go as fast or as slow as you want me to today. So. Choose more of the similar types of problems. And we just have a different graph. So the first one, we're looking at the limit as x approaches 1. 1's right here. So our limit would be at 2. Nothing tricky on that one. And we've got the limit as x approaches 3 from the left. So that's coming in here. So our limit coming in from the left is 1. There's 1. And then the next one, we're going to approach 3 from the right. So coming in this way. What's that limit? What's our limit there? Oh, we got our answer got distracted. Nobody else is stepping up. That one's 4, right? Y value 4. So then D part says what's our two-sided limit? D and E, yeah, because the one-sided limits are not equal. D and E. E part says find f of 3 is 3, yeah, right here. That's a 3. 3 of them. Let's see. Number 3 has a ton of parts. They're not long. So there's our graph. Let's see. First limit, we want the limit as x approaches -3 from the left. So that's coming in right here. So our limit there is 4. Next one, we're going to approach -3 from the right. Coming in that way. So again, that's 4. And then C part says what's the limit as x approaches -3, the two-sided. What's it going to be on this one? 4. Yeah, since they both match, that's our two-sided limit. 4. Okay. D part says what's h is what they're calling our function of -3. So that's right here. So we've got a hole there. And so it's not defined there. So we would, in the web assignment, we would say D and E, or you could say undefined. And I think we're going to go through a similar process here, just at 0. So 0 from the left, 0 from the right, and 0. As we're approaching 0 from the left, the limit's 1. We approach 0 from the right, the limit's -1. Yep, I covered the graph up there. -1. So the two-sided one does not exist. Not exist. And then the last part wants to know h of 0. So what's our function value right here? That's right there, at 1. And then I'm guessing we're doing 5. Oh, we got 2 and then 5. So limit as x approaches 2. What's that one going to be? 2. Yep. 2. And then what's those next? It says h of 2. So what's the actual functional value at 2? Yeah, the NE. And then we want the two-sided, or we know from each side at 5. So we want the limit as x approaches. First one is 5 from the right. That one's a little weird, but we're coming in, approaching 5 from the right. So where does that look like we end up? Yeah, end up with 3, right? End up with 3 on that one. And then coming from the other way, the x approaches 5 from the left. Yeah, we got an issue there because we've got this oscillation. Since we have this infinite oscillation, does not exist. Does not exist. Questions on any of those? Getting them off the graph? Yes. Well, yeah, it's hard to tell. Just if you see it bouncing back and forth, you can just assume right now that it's infinite. Yeah, I mean it'll have this slinky look to it. That's probably anybody even know what a slinky is in here? You do? Okay. Yeah. Other thoughts or questions? Yeah, it'd just be, yeah. So there might be like one graph that's got several things going on, and you're just looking at the limits at several places. I just picked these 3 off WebSign because they had different things going on. Like that one had the oscillation, and the other ones didn't. Anything else on those before we move on? Okay. Or we get kind of into thinking about limits without a graph. So on one like this one, and we know if we plug 5 in, we're going to get 0 in the denominator. So that's going to give us a vertical asymptote. So we're just trying to figure out which way does it go. Does it go up or does it go down? So we're coming in from the right side. So you can just plug in test values here. We're trying to approach 5 from the right. So what would be a good test value for x? We're trying to get close to 5, but we're coming from the right side. Yeah, 5.1 maybe. Could try that. So if we do 5.1, and on the top, we're going to get 11.1. And on the bottom, we're going to get 0.1. So how's the sign work out on there? Is it going to be positive or negative? Positive, so we're going toward infinity. Yep. Well, yeah, you can, but you have to be careful. It's not going to be negative on bottom if we're to the right of 5. It'll be positive on bottom. But yeah, if you can look at it, you're okay. Yeah, so you don't get away with that in math class a lot. Okay, but just saying, well, I just looked at it and figured it out. But the technical term you'll see used by that is I solved it by inspection. So it's okay. Sometimes you'll see you'll see directions that say find the limit by inspection. So sometimes that's all we have to do. That's okay. That's going toward positive. What if it was approaching 5 from the left? Then we would have to try something like 4.9. So then on the top, 10.9, and then on the bottom, 4.9 minus 5. That. So if we're approaching from the left, it's negative, so it goes down. So we know the graph of this thing, as we get close to 5, from the right it goes positive, and from the left it goes. Okay. 5, same kind of problem. On this one, we're looking at both sides, though. We're looking at both sides, so we need a test value. If you're doing test values, you need a test value on both sides. So, or you could just figure out the sign. Okay, if you want to do it that way, that's fine. So maybe like on the right side, try 6.1. See what happens. So if we do that, then on the top, for sure, it's going to be negative. And then on the bottom, we're going to have like 0.1 squared. So that's going to be positive. So coming from the right side, going down, negative. Okay, so we'll say if we plug that in, we're going down. And then we need to double check on the other side. It might not be multiple choice. So if we're coming in at like 5.9, then on the top, it'll be negative again. On the bottom, we'll have some small number squared, so it's going to be positive, so it's going down again. So they do match. They're both going down, so this one. That's 6. Evaluate the limit using the appropriate limit laws. I'm not going to make you break it down into every little piece. It's basically just going to be find the limit on one like this. And if you know, you can use the limit laws. So on this one, what's the first thing we should try? Yeah, direct substitution. We should try that. So if we try direct substitution, let's see, 2 to the 4th, 16. On the bottom, negative 2 squared will be 4, times 2 is 8. And then negative 2 times negative 3 is positive 6, 1. So 14 over 15 if I did all that right. Okay, it worked. No problem. So that's using the limit laws. So using the limit laws, we're saying we can break it apart into pieces, and it works out that way. 14. Okay. Number 7. What's the first thing we should try on this one? Direct substitution. That's almost a trick question. That should be our first attempt. Okay. We're trying to approach 2 here. So let's see. 2 squared is 4. 4 times 3 is 12. On the bottom, we'll have 10 minus 1. So what do we get there? 16 over 9. And then if we simplify, yeah, 4 over 3. Sit on that one, yes. Well, so you can take square root of the top over the square root of the bottom, and they're just both perfect squares. So square root of 16 is 4, and then square root of 9 is 3. It might be like a minor thing. It depends on if I tell you, to simplify. The important part is really this piece, where you can direct substitute to get it. And then after that, it's arithmetic. So slightly less important since we're in calculus class, not arithmetic. Okay. Let's see. What's next? All right, we want to find where our graph has a discontinuity, all the places, and then figure out if it's continuous from the left, from the right, or from neither. Okay, so if we're starting over on the left, where's our first discontinuity? What x value? -4. Yep, and that's a discontinuity because we have a hole. Right? Would be our informal name for that. Okay, and then what about, is it continuous from the left or continuous from the right? Or neither on that one because it's undefined there. So if you try to come in with one-sided continuity from either way, you're still going to be undefined there. So it's not continuous one-sided either. Then next discontinuity, where's it going to be? -2. We got to jump there. And then what about the one-sided? Would it be continuous from the left or from the right or neither? This one is continuous from the left because if we're just looking at the left portion of it, we don't have any problem because we're defined there. And if we try to come in from the right, we would be undefined at our endpoint. So not continuous from the right, but it is continuous from the left. Next discontinuity, which one? 2, yeah. So 2, again, we have a jump. That one is continuous from the right because it's defined there, not continuous from the left because it's undefined. And then next one, 4, we have a infinite discontinuity or a vertical asymptote, if you want to think about it that way. And then what about the one-sided continuity? Continuous from the right, not from the left because it goes down toward negative infinity, right? But it is from the right because we are defined there. Okay. Questions on that one? And had all 3 types of discontinuity in it. Okay. Look at the next one. Okay. So this one really we're just trying to remember our definition of continuity. So this we're discontinuous, -3. And the reason that happens is we get 0 in the denominator there. So what are our 3 things we have to have continuity, the long version? The function has to be defined at that whatever particular x value. So here, would this function be defined at -3? Nope. And then we need the limit to exist at the x value. Would the limit exist on this one? Well, you could say it's infinity. Say it's an infinite limit. And then we would need the 2 to be equal, right? The functional value and the limit to be equal. We can't have that because we don't have a function definition. The main takeaway on that. And then the graph, we can think about the graph. So for sure we're going to have a vertical asymptote at -3. So think about a test value of 4. Okay, so then we'll have, oh no, yeah, let's try something closer. I don't know where I got 4 from. So we're trying to approach -3, right? So like let's do like -3.1. So slightly to the left. And we'll have positive on top, negative on the bottom. So that means it'll be going down on that portion. And if we pick a test value slightly on the right, 2.9, and it'll be positive on the top and positive on the bottom. So this will be going up. On the left side it's going down, right side is going up, and we're at -3, not 3. So let's see. That one looks good there. Is that what we said? Down on the left? Yeah. Down on the left, up on the right. What you got? That's because WebDesign's dumb. I don't know why I'm that section with the infinite limits. So saying that a limit is infinite, and when you're out at infinity, is saying there is no limit because it keeps getting bigger forever. So I don't know why sometimes they'll let you say infinity and then sometimes they make you say D and E. I'm not sure why. So when you're saying that a limit is infinite, you're really saying it does not exist, but you're being a little more specific. You're saying it does not exist in a specific way. It's not going to be an issue on paper test. It's just that particular section of WebDesign. Okay. So picking some more limits off the graph. Okay, so this one, the first one, we want the limit as x approaches infinity. So the extreme right. Here's the x-axis. So what's it look like? Yeah, -2. Like we've got a horizontal asymptote at -2 there. Okay. And next we approach negative infinity, so the extreme left. What's it look like? Yeah, it looks like we got a horizontal asymptote at 2. And then let me guess, they got approaching 1 and approaching 3. And there we go. So as x approaches 1, what would we say about our limit there? Infinity. And then at x equals 3, that one's going toward negative infinity. Big takeaways on that one. But if that one gave you trouble in WebAssign, we ran into this on Friday. It's because it wants you to give the asymptotes as x equals for the vertical and y equals for the horizontal because it says equation. So it won't let you just put in the values there. So 11, we're picking out a graph. We got these conditions. We want the limit as x approaches 0 to be negative infinity. So let's just start with that one and see if we can eliminate any. Okay. So as x approaches 0, we want to go toward negative infinity. I'm not seeing that on the first graph. What do you think about that one? Maybe it goes down. Okay, so I'm marking off this one. Okay. And what do you think about that one? No, because one way it goes up, one way it goes down. And then third one, maybe. Okay, let's see what else it says. Depends on if they're not showing us the whole thing or not. So then we've got the limit as x approaches negative infinity is 3. So that works for that one. Let's see. What about that one? We go toward negative infinity is the limit 3. No, because this is the x-axis right here. So not that one. So really on multiple choice, that's all we have to do. But let's check the other one. It says the limit as x approaches infinity is -3. That one does meet all the criteria. It said As we approach 0, we should go to negative infinity. As we approach negative infinity, we should go to 3. And as we approach positive infinity, we should go to negative. Got all those. Be prepared. Probably what I'll do is I'll probably give you a blank graph, and I'll say, maybe not 3, but I'll give you like 2 of these and say sketch a graph. Has those limits. So infinite number of answers. Just got to make sure you meet the limit there. Oh, number 12. Yeah, I don't think we're going to have any trouble getting through all these. 12 says evaluate the limit using the appropriate properties of limits. Have a limit as x approaches infinity of a rational function. So what should we do? We could get an idea, yeah, for sure. We could try plugging in a really big number and give us an idea of what the limit's going to come out. And there's even a shortcut. We can know what the answer is going to be. What's the answer going to be? Everybody remember the shortcut? The answer is going to be 4 over 3. Yeah, because the degree of the top's the degree of the bottom that match. And we want to show it, though. And so what's our calculating method? What do? We divide by the biggest power of x, where? In the denominator. So we take and divide everything, in this case, by x squared. So 4x squared over x squared would give us 4. Then we would have minus 3 over x squared. Bottom 3x squared over x squared will give us 3. And then we'll have x over x squared will leave us with 1 over x minus 3 over x squared. And we're dividing by this one. So then what happens here? Anytime we have a number over a power of x and we're approaching infinity or negative infinity, what's our limit going to be? 0. So this one goes to 0. This one goes to 0. This one goes to 0. The only thing that's left is we need the limit of 4 over 3. The limit of 4 over 3 is 4 over 3. Just divide by the largest power of x in the denominator, and then remember that property that anytime we've got something over a power of x, a number over a power of x, it's going to go to 0. Okay. 13. Similar, that we're approaching negative infinity. So we just have to keep an eye out to see if there's anywhere where that's going to make a difference with the signs. On this one, using the shortcut, do you remember what it's going to be? 0. Okay, let's show it. So what are we going to divide by? Yeah, we're going to divide everything by x squared. So x over x squared, 1 over x, minus 4 over x squared. And then the bottom, x squared over x squared is 1, plus 8 over x squared. There we get 0, 0, 0, so that's 0 over 1, which is on that one. Okay. 14. Same type of problem. Throw this a little bit of a curve because we've got that square root involved. So what are we going to divide everything by on this one? x, and then we also need to keep in mind that if we're inside of a radical, it's going to be x squared that we use. And that's okay because x is on the positive side. If we were approaching negative infinity, then we would have to use a minus sign up there. Pick which side you want to write that on. You can that way too. But we don't have to worry about that on this one. So in the top, we're going to inside the radical, we're going to divide everything by x squared. X over x squared, 1 over x. And then 3x squared over x squared, 3. In the bottom, since we're not in the radical, we'll divide everything by x. So 8x over x, 8, minus 1 over x. And then there's a 0. There's a 0. What do we end up with? Yeah. Square root of 3 over. And could have checked yourself with the shortcut on that because square root of x squared would be x, so these would have the same degree. Root 3 over 8. But I need to see this. Questions on that one? Yeah, and when we're underneath the radical, we use x squared. And then if we're not underneath the radical, we can just cause initially what we really are doing the first step is in the top we would have that, and then we'd have the stuff in the bottom. But to make any headway, we need to move that inside the radical so we can simplify those things. That's where the x squared comes in. Mm-hmm. 15 gives us a parabola, 5x minus x squared. Let's find the slope of the tangent line to the parabola at the point 1, 4. Okay. So this is similar to the one we started out with. Our x value is going to be 1, where we want our tangent line. So we got 5x minus x squared. I'm going to rewrite that here. We can have some room to work over here. What we want for the slope of the tangent line, using the limit definition, we want, I'm going to call this f of x so it matches up instead of y. Okay, so we want f x plus h minus f of x for h. So our x coordinate, 1. What we want is this limit on f of 1 plus h minus f of 1 over h. So I'm going to move it over here one more time. When we fill in, we'll have 5 times 1 plus h minus 1 plus h squared and minus You can go ahead and fill in, you figure out what we get for f of 1 if you want to. So that'll be 5 minus 1, 4. Over h. We just have to simplify this thing so we can find our limit. Okay, so let's see this 5 plus 5h minus 1 plus 2h plus h squared minus 4h. So let's see. Be careful with the signs. Right. So 5 minus 1 minus 4 goes away. And will leave us is minus h squared plus 3h over 4. Is that looking okay so far? You don't see anything I messed up yet? Then, oh, not over 4, it's over h. How'd that turn into 4? Over h. And then we can cancel one of the h's, factor it out and cancel, so that'll leave us with minus h plus 3. So what's our limit? 3. That's the slope of our tangent line at this point, 1, 4. So slope is 3. Second part wants us to find an equation of the line. So we take our slope, our point, plug in, so y minus 4 equals 3, x minus 1. Tells us on this one it wants it solved for y, so let's see. 3x minus 3 plus 4, so 3x plus 1. I'll give you that just because it'll make me upset if it messes you up if you did that wrong. So I'll give that part to you. And then we want the graph of the parabola and the tangent line. Not this one, why? What do we know about our parabola? Yeah, I got a negative leading coefficient, so it's going to be opening down. Don't have to worry about that one. Could be that one. Definitely not this one because the tangent line doesn't have the right slope. Not going to be this one, why? Negative slope on the tangent line, so yeah. Questions on that one? Yeah, they get all this stuff over here. Yeah, for sure getting the slope of that tangent line is the messiest part at least. You got what you need? I'll be glad to scroll back wherever we need to later. 17 we got, 16 is next. It's the same type of problem as that last one we just did. It doesn't have all the steps. Is find an equation of the tangent line to the curve at the given point. Point's 9, 3. Okay. So function square root of x, and then we want the point 9, 3. So let me so we want the limit h approaches 0 of our x coordinate this time is 9. So f of 9 plus h minus f of 9 for h. This one's not quite so messy. The limit of 9 plus h, just the square root of 9 plus h, minus, I may have spoken too soon, minus square root of 9 for h. Okay. I don't think we've done one like this, have we? What do we have to do to find our limit on this one? Do square root of 9 and multiply by the conjugate. So square root of 9, I'll call that 3. Multiply by the conjugate. I didn't mean to give you one this messy. Right here. I just wasn't paying close enough attention. So then, what do we get there? So that'll be 9 plus h minus 9 over h times this. We don't have to multiply the bottom out. Maybe we did do one like this. I don't remember. So we got a common factor of h on the top and on the bottom. Cancel those out. That'll leave us a 1 on the top. So what's our limit? We plug in 0 for h. We get square root of 9, 3 plus 3. Yeah. 6. Our slope. That's not horrible. I just don't remember us doing a lot like that. And then finish out our slope is 1 over 6. And let's see. That is minus 3 over 2, and then we got to add 3 to the window 1/6x plus 3 over 2. That was messier than I intended. Questions on that one? Don't. I'm not gonna give y'all hard ones or anything. It just turned out we had to rationalize on that one and do that on purpose. 17 we got out of the way. That was one of the more challenging. 18, we're matching up derivatives with graphs. These can be tough if you don't know what to look for. So these are the derivatives. We're trying to match them up with their function. So things to look for, like if I'm looking for a here, I'm going to say, well, my derivative is negative, and then it's going to be 0 at some point in here. Then it goes positive, and it's going to be 0 again somewhere right here, and go negative again. So we go negative, go through the x-axis, take a turn while we're positive, and then go back through the x-axis. So which one's that one going to be? 3. That one's 3. This one and this one. Maybe one that's easy to do first. If you're looking at the derivative first on this one, we've got a positive derivative. We've got some point where we don't have a derivative. Negative derivative, some point where we don't have a derivative, and then it's positive again. Which one's that going to match up with down here? Because we've got positive slope, no derivative at the corner. Negative slope, no derivative at that corner, and positive. So those two. That one, that one. Then on these two, you can really just look at how many times our derivative would be 0. So like on D, we'd have a 0 derivative right here. And then go down and have a 0 derivative at the bottom of the valley, 0 derivative at the top of that peak. So we got to go through 0 3 times. So which one of our two derivatives left goes through 0 3 times? Okay, we got 1. And we'll do a triangle. How about? And then the other one, just to think through it, our derivative is close to 0, but then it's negative, and then it does go to 0, and then goes positive and gets close to 0 again. So questions on thinking your way through those? And what we got left? 19. Want to know where our graph's not differentiable? Woo. Oh man. Somehow I scrolled all the way back up to the top and it quit working. When we get scrolled back down there, we want to know where our graph's not differentiable. So what kind of features can our graph have that will make it not differentiable? What can we have on our graph? One, right? We can have a corner, or a jump, because not only do we have to worry about just things that make it not differentiable, but there are things that make it not continuous, and if it's not continuous, it's not differentiable. All right, so we've got the discontinuities. We have jumps, or we have vertical asymptotes. We'll get those discontinuities there. Okay. All right, and then what else? We've got corners, or what I call a cusp. The textbook lumps that in with corners. Okay. Or we have one more situation. What kind of tangent line? What kind of tangent line would have an undefined slope? Vertical. So if we have vertical tangent line. So on this one, it's a little bit tricky with this graph. It almost looks like we would have a vertical tangent line in here somewhere, but it's not quite. So it helps that it only gives us 2 spots to worry about. So where would our function not be differentiable? Yeah, -4. Now we've got a corner or a cusp, whichever category you put that into, and then where else? 0, because we've got a jump there. We have a discontinuity, or a corner, or a cusp, or a vertical tangent line. It's not differentiable. All right, how you feel? So. Anybody terrified? They feel like they're in real bad shape now? Okay. Somewhere in the middle? All right, well, that's it. If you have other questions, feel free to hang around. That's all the practice test stuff, though. I'll be glad to hang around if you